Okay, so thank you for the introduction, Duco, and hi everyone. So, as it was said, I'm Adrien BIBAL. I'm a postdoctoral research fellow at the University of Colorado at the Anschutz campus. So today we will talk about attention, so the attention mechanism present in neural networks. And in particular, we will see how attention can be used to explain these neural networks. So just a first note before starting, the presentation that I'm doing right now is based on an ACL presentation that I did at ACL 2022, which was based on the paper Is Attention Explanation and Introduction to the Debate. So that's the question that we will consider in this talk too. Okay, so first of all, many black box complex machine learning models are used today, mainly because of their performance, but for many other reasons, like legal reason or trust or something like that, we need to explain these black boxes. And there are multiple ways to do that. So we can use post-hoc methods, meaning methods that are like external to the model in order to get an idea of what's inside the model. So that's very useful when we don't have any access to the inner workings of the model. But we can also use the internal components or metrics that are like used or trained, learned during the training process of the black box to explain the black box. So in our case, we will consider attention in neural networks, and attention belongs to the internal way to explain the model because it's something that's inside the model and trained with the neural network as a whole. So what's interesting with that is that we can have an explanation of the black box which is trained alongside the black box itself. So it can be more interesting to consider an explanation that comes from the inside of the model instead of something that's outside and just approximating what the black box is doing. So there are different ways to compute attention weights in the literature. The main ones are additive attention and scale dot product attention. But in this presentation, I will not go into these details, and I will just mention the fact that it has been shown in different papers that the results are roughly similar, and the conclusions related to the debate that I will mention are roughly the same with this different way to define attention. So it's not really important to know which one of the two or other ways to define attention, which one is used to gain some explanation about the black box. So, at start, we will consider a debate that started in 2019 by Jane and Wallace and Wigriff and Pinter, so two papers. And they consider the question, can the attention values or weights in the attention layer or layers can they really be considered as an explanation of the model? The thing that has to be considered is that before that point, attention was mainly used as an explanation because it seems like an explanation of what the black box was doing. So, first of all, attention was created for performance purposes, and it worked really well. And then we saw that attention could be used to gain a certain explanation of the black box itself. So it was used like that. And in 2019, these two papers started a debate. So they are not the only one that discussed the fact that maybe attention cannot be used as an explanation, but they started a debate in the literature where different papers started to provide different insights about this question and this debate. So the first paper, the one from Jane and Wallace, started with two arguments. The first one was that attention does not always correlate with saliency maps. And the hypothesis here is that saliency maps is somewhat wrong tool to assess explanation. So as attention does not correlate with this technique that's really well known and relatively trustworthy, then we can say that there is a problem at least with the fact that attention does not correlate with it. The second argument is that you can obtain the same outcome. So for one input, you obtain the same outcome with different explanations. And the different explanations are obtained by shuffling the weights, the attention weights. So for Jane and Wallace, it's a little bit weird that you can, for one input and one output, shuffle the weights and obtain different explanations for the same, basically, input-output link. That's a little bit weird. While in the black box, you will expect to have maybe one explanation in the black box. So from this paper, there were different papers, but mostly one other one, which is the one from Wigriff and Painter, which responded to these two arguments. So for the first argument, they agreed with the fact that attention does not correlate with that saliency map, and that thing is an issue. But on the second point, they had two counter arguments. So first, they said that shuffling weights do not always produce real models. So by real models, I mean models that could be obtained through the training process. So as you don't obtain real models or models that can be obtained with training, it's not really fair to judge or to assess the quality of attention as an explanation like that. The second thing is that for them, so for Wigriff and Painter, the fact that attention can produce different explanations for the same outcome is not a problem. It's like in reality, you can have different views of the same event, different explanation of the same event. So in the end, attention provides an explanation and not the unique explanation of what the model is doing. So having different explanations for the same outcome is not really a problem for them. So starting for these two papers, there were different pockets in the literature that started to analyze the debate with different point of view. I say pockets because these different areas of the literature do not always discuss with each other and cite each other. So they're pretty much isolated. That's not the case for all papers, but what was interesting to do in the ACL paper that I mentioned at the start of this presentation is to expose the different pockets of the community of the literature so that we can talk with each other and that we can have a better view of the debate as a whole. So first pocket that I will mention here is the additional arguments that are provided against attention use as an explanation. So our first paper from Serrano and Smith showed that if you remove the important features, so the important features that are said as important by the attention mechanism, removing these important features does not always lead to a decision flip. So that's something that's a little bit weird because you could expect that if you remove what's considered important for a decision, you will have another decision. But in fact, it's not always the case. And worst, in fact, removing important features with other methods, other explanation methods, like gradient-based methods, in that case, you have a decision flip with this procedure. So that's something that goes against attention. and that can suggest that attention is not a good way to explain what the model is really doing. Another thing is that LIME, so one of the techniques that can be used post-hoc, so external to the model to explain it, LIME can provide good explanations as being external to the model when attention, which is internal to the model, can't. So that's a very, very strange thing to consider, as we generally use attention because it's trained alongside the black box that we're trying to explain. And this thing that's internal to the model is worse at explaining the model itself than something external. So this means that the first argument of Jane and Wallace about the fact that attention does not always correlate with things like saliency maps also holds for other techniques like LIME. And in fact, it also holds for other techniques like Shapley values. So again, it's very, very strange that techniques that are external to the model, but even other techniques internal to the models do not correlate with the explanation provided by attention. The second pocket of the literature that I will consider here in this presentation concerns the theoretical analysis around the debate. So the first pocket was really adding arguments about the fact that attention cannot be used as an explanation. And here we are more in the analysis of why it is the case that attention cannot be used as an explanation. So our first explanation comes from the fact that there are issues related to biases in the embedding. These issues are explained by something called combinatorial shortcuts, and they, in their paper, Bay and al. Show that if you add tokens in all documents, so here we are in particular in natural language processing, if you add the tokens A, B, and C, for instance, in all documents, you can see that some attention is put on A, B, and C, even if they are present in all documents. So if they are present in all documents, they should not be used to discriminate for classification or something like that, because they are present in all documents. But the fact that attention is put on these tokens means that there is something other than the use for the task in the attention that is put on this token. And what you can find, for instance, is that in the embedding of your input tokens, so words or here ABC, there is a relationship between the input token that you are embedding and the outcome of your, let's say, classification. So if your outcome is a positive classification and the embedding of the token A somehow contains something that's positive, then you will have some attention that's put on A because of the bias related to the positiveness in the embedding. So it's not useful for the task itself, but there are some biases that makes them interesting, so these tokens, that makes them interesting for attention. Another thing that's important is that when you are embedding input tokens, in particular, again, in natural language processing, you are in fact embedding each token with its context. So you have multiple tokens that influence the representation of each individual token. So if one token is a word, you will have the other words of the sentence or even the paragraph that are influencing the representation of the token that's considered by the attention layer. So what that means is that when we look at an attention map to see which word is important when making a decision, in fact, what we are considering is each word individually, because the weight is put on each word, and we will consider the explanation like that. But what the attention is saying is that this word and its context is important for the decision. So it's really difficult to extract the word from its context when the explanation is done. And another thing that's really interesting and that has been studied in several papers is that we can, in fact, find the thing that we want, so the explanation in attention, if we decompose the weights in two parts. So one of the two parts is really the explanation that we want, and it's called effective attention by these authors. Now there are a third pocket here that considered if the conclusion of the debate holds for different tasks. So one first result about that, which was really interesting, again, it's really focused on natural language processing, is that attention may not be explanation for single sequence tasks, meaning tasks where we have a single sequence in input and producing, for instance, a classification as output, but for other tasks that are considering multiple sequences, like machine translation, where you have a sequence as input, for instance, a starting language and a target language as output. Then, if you look for the explanation provided by attention, you get a better correspondence with other feature importance measures. So the conclusions of the debate are not the same for all the tasks. There is another thing that's really interesting in transformers. In analyzing different tasks like syntactic dependency tagging and co-reference resolution, you can find, in fact, that the model learns something that's relatively common between the tasks to solve these different tasks. So in the case of birds, the authors here have seen that the attention heads of birds encode syntactic information about the language that's used to solve the tasks. So here we don't have a local explanation, which is an explanation of a specific instance. So for this specific instance, what's the outcome, what's the classification? But you have a global explanation of the whole model. Here, what the heads of birds are doing. And what's interesting is that you can have a global explanation across different tasks, like part of speech and syntactic tagging for GPT-2 also. So that's really interesting. Okay, now a big issue in the literature and in the debate is related to the evaluation methodology. So we have some papers, like the one from Zhu et al., which comes with the fact that manipulating weight does not always produce Turing models, as we've seen already with the starting papers of the debate. But some of the papers are mentioning other things that are more surprising. Like here, the fact that other explanation techniques, like line and SHAP, in fact, do not always agree with each other. So as they don't agree with each other, should we consider the fact that they don't also agree with attention? So the fact that the different techniques don't correlate with each other means that maybe we should not use correlation as a way to assess if attention is a good way to explain or not. Because by doing that, we will also discount many other explanation techniques. Another thing that's really important is that explanation, in fact, is not well defined. So if it's not well defined, can it be fairly evaluated? That's not sure. And on the same line, there is a thing that's not always distinguished in all these papers, which is the distinction between faithfulness and plausibility. So the faithfulness of an explanation in machine learning means that the explanation is close to what the model is really doing. And that's what you want with an explanation. You want an explanation of a deep learning model to be close to what the deep learning model is really doing. Otherwise, it's not really an explanation of the deep learning model. So that's faithfulness. Plausibility is more concerned with users. And it's saying that the explanation should be plausible for the user. And that's really important too, because if we have an explanation that's really close to the black box model that we are trying to explain, but the explanation is not usable, understandable, or plausible for the user, then the explanation is not really useful and it's not really an explanation. So you both need to be close to the black box, faithfulness, and to be understandable and plausible for the user. So it's plausibility. And you often find the two in the papers that are analyzing attention as an explanation. And sometimes, even if the two are considered, the papers that are evaluating attention are not grounded on the same assumptions. So there are many, many issues related to assumptions and definitions in the evaluation of attention as an explanation. Okay, now there is another way to evaluate explanations. You can use user-based experiments to have an idea of the power of attention to explain the black box models. So if you ask, are the top 3, I guess, weights provided by attention really relevant? And you ask that to users, you will often find a very good correlation between the top 3, I guess, weights provided by attention and what the users consider as important. So they will agree with each other, so the attention from the machine and users, which means that attention weights seem to be plausible explanations. You can also ask, what are the most important words in these classifications? You can ask that to users. And again, you will find that attention weights seem to be plausible explanations. So if you take the distribution of importance provided by attention and the distribution of importance provided by users, these two distributions, in fact, are very similar. So that's very important because it's saying that attention is plausible or as something that's somewhat plausible for users. And what you can also find is that even if you use eye tracking attention by tracking the eyes, there is, again, a similarity or a correlation between the machine attention and the attention of users through eye tracking, at least on easier tasks. What is considered for complex tasks or more difficult tasks is that users will often use different strategies or more complex strategies that attention cannot grasp, let's say. The important note here is that the fact that attention can be a plausible explanation does not mean that's a faithful explanation. And that's something that has been demonstrated, for instance, by Prutti et al. In their paper, where they built a model to be biased, but the explanation does not show these biases from the model. But the explanation still is plausible for users. So the users will say, okay, so this explanation is not biased and is plausible for me, so it's a good explanation for me as a user, but in fact the model is built to be biased. So the explanation is not faithful because it's not showing the biases of the model. So you can have a plausible explanation, something that's plausible for the user, but that's not really faithful to what the model is really doing. So now I will briefly talk about some solutions that are proposed to solve these problems. So mostly there are technical solutions to make attention more faithful and user-centered solutions to make attention more plausible. Of course, there are technical solutions for the plausible explanations, to obtain more plausible explanations, but they are not widespread. So for faithful explanation, we can add new parameters like a score SI that will counterbalance the attention weight if it does not weight the representation of the input token I. Here it's HI. So if it does not weight the representation in a good way, given the biases that we discussed earlier. We can also weight the input to counterbalance the problem of combinatorial shortcuts. So with the A, B, C that are added in all documents, we can regularize to the model to enforce the link really between the attention weights and their corresponding input token. And we can use different techniques like orthogonalization between the embeddings so that they're different than their context. We can add penalty terms to make them different from their context too. And we can even penalize non-faithfulness in the model. So quickly, the strategy 0-1 max is in fact a strategy where we consider the maximum weight, the weights that have the maximum value or the biggest value, let's say, in the attention layer. We make them a zero, and we check if the output is the same. If the output is the same, then maybe the attention was not faithful, and it should be penalized because of that. So that's one strategy. There are many others to penalize non-faithfulness. You can also work toward plausible explanations with users by supervising attention with user-provided attention. You can also include user feedback in active learning fashion. So adding information from user until you have something that's really plausible for them. And you can use user attention in a Bayesian framework to gain more plausible explanations. So there are more information about the paper. I didn't mention everything, of course. You can find many different things, like the different tasks that have been considered in the paper that I mentioned and the one that I didn't mention, the architectures that have been used, so BERT, LSTMs, and architectures like that. So you can find all of that in the paper. I will finish with elements of discussion. So the first point is the question, is attention needed at all as an explanation? As I said earlier in this presentation, attention was originally built to have better performance. So as other techniques are built for explanation, maybe we should use attention for the performance and other techniques for explanation. It's not clear the reason why attention should be needed for explanation. Maybe it's a really good thing, but that's something that should be argued. And the other thing is that both faithfulness and plausibility should be evaluated, even if it's not always the case in all papers. This should be evaluated together because one of the two only is not sufficient. Another thing is the question, but how to evaluate faithfulness? Because faithfulness is how close my explanation is to the black box. But by definition, I don't have access to the black box. That's why it is a black box. So as I don't have the ground truth about what the black box is doing, otherwise I wouldn't need explanations, I cannot really evaluate if the explanation is close to the black box. That's a very difficult question, and that's need more studies in the literature. We have seen in the literature that there is no common ground when discussing on the debate, so the architectures are always different, the tasks that are used to evaluate are always different, and we have seen that there are like interesting leads to obtain faithful attention, like effective attention, weighting, transforming schemes and stuff like that to obtain more faithful attention. And you can also supervise the attention to improve the plausibility. So you have leads to improve the explanatory power of attention. I want to say one word about transformers. I don't have time. I just said that they are not very studied in the literature. Maybe it's because they are very complex. Even if we have interesting findings like the ones with the heads, the different heads, the attention heads of BERT. In conclusion, there are multiple things to do next on the subject, like refining different concepts, like the ones of faithfulness and plausibility, developing a common ground in the evaluations so that we can be sure that we're talking about the same thing. and extending studies about the strategies that are already developed, like effective attention for faithfulness or integration of users in the loop for plausibility. And why not combining all these results to produce, for instance, a supervised effective attention? So that's it for me. I have a bunch of references in these slides. They are all in the paper that I presented at the start, so you can find them there. And thank you for your attention.
Thank you. I guess we may have questions in the room.
I already discussed with him.
Yeah, that's come on. Can you raise some of the points you discussed with BIBAL then?
I will try.
I have a question. Can you hear me?
Yep.
Yep.
So this is mostly about text, but is there a difference with VITs, for example? Does it work the same, or has it been explored, the idea of attention in video transformers?
Well, I'm sure there are many things in the literature about other data types like tabular data, images, videos, and stuff. Here we consider the debate that was started by the two papers that I presented, and in fact, this debate is rooted in the NLP community. So most of the papers that are talking about this debate are in fact in the NLP community. So my guess is that all these findings also apply somehow to other data types, but most of the works that I presented, if not all, are rooted in the NLP community. But we have some elements that are like very generic, like the problem related to faithfulness and plausibility. That's even something that's not related to attention at all. It's related to all possible explanation methods. So you need explanation methods that are both faithful and plausible, and that's not something that really studied in the literature. And if you say that attention is not explanation, you should say that it's not faithful, or it's not plausible, or it's not both of the two. But you have to say something about that, and that doesn't matter if the input data is a text or a video or something.
Okay.
So I'm sure these issues are also present in other literatures about other data types.
Okay, thank you very much.
Questions here?
I may have one question. Can you hear me?
Yep.
Okay. Not really a technical question, but I was wondering if you had some real life examples of the usage of interpretability of transformers, for example. You mentioned, yeah.
Sorry, yeah.
Yeah, you mentioned things about the legal domain, but is that really something which is really used? Well,
so there are at least two questions or two answers. First one, the one about transformers. So as I said, there are a few papers on transformers, and one of the reasons is that it's not easy to find explanation in these transformers. So most of the papers only provide global ID, but because you have many attention heads, so heads that are looking at different things in the document, in the image, and element like that. In the image, it's maybe easier to grasp because you can see that the different heads that are looking at one here of a person and the other here of the same person. So you have to look at different parts of the image and stuff like that. But it's really difficult to understand the interaction between all these heads. So it's sometimes really difficult to understand what one attention layer is doing. So multiple heads is very difficult to grasp.
But even with techniques like lime or sharp, I mean, it provides some kind of an explanation. You've discussed about the relevance of this explanation, but I mean, for the end user, has it been really used somewhere? I mean, people are saying, okay, we need some interpretability, but do we really need that? And at some point, isn't plausibility all we need? Do we really need the exact explanation of why the neural network predicted this class? Have you got some real life example of that?
There are many examples. For instance, in recommender systems, like in Netflix and other systems, they need to provide the reason why they recommend one thing or one other thing. Otherwise, the user will not trust the recommendation and will not use the system. So that's the trust reason that I was mentioning at the beginning of my presentation. And for the legal reasons, so that was another part of of your question. It's not really the use of explanation in the legal domain. It's rather the fact that there are legal obligations to provide some explanation. For instance, when you are refusing a credit to someone. In some countries, if you refuse the credit to someone and you used an automated system to determine if the person in front of you can have the credit or not. If you refuse it, you have to provide the reasons why the credit has been refused. So if the automated system has been used, you should provide an explanation of what why the automated system predicted a no for the credit. So there are different reasons like that that are like that makes explanation really useful or mandatory in real life.
Yes, thank you.
Yeah. Another question?
Okay, I have a question. I don't know if this question would be the same with the content, but as we saw that the debate is around the explainabilities in natural language, I wonder whether the transformer in visual domain or in multimodality use the same problem in explainability. I don't know if you have a look in other domains.
Yeah, as I said earlier, I'm convinced that the problems are similar with all the data types. But here I studied specifically the papers that talked about the debate. The reason for that is that they were, as you saw, it was already difficult to have a common ground between all these papers because they were talking about explainability and attention, but with different definitions, different architectures on different tasks, and all of that rooted in NLP. So it's very difficult to analyze all of these papers, but at least they all mention the same debate and they all take position in the debate. So that's the common ground that we use to consider the papers. Otherwise, there are like, I don't know, thousands and thousands of papers mentioning attention and explanation. And with a lack of common ground, it's difficult to make them discuss together. So maybe another paper that can be done in the future is to see, as I've shown in my presentation, we can have different conclusions given the different tasks that we're analyzing. But maybe we can have even different conclusions with the different data types. So maybe that's something that can be done. For instance, I said that there are big issues related to biases in the embedding, but the way images or videos are embedded are not the same. It's not the same way as text. So maybe you don't have all these biases in images or videos, or maybe you have other issues related to biases and stuff. So That can be another thing to analyze. But here we really focused on the papers that were mentioning the debate and that took position in the debate explicitly.
I have a question. You mentioned that attention was more understandable on at least machine translation task rather than with a single sequence task. But you mean machine translation, so the attention is only unidirectional when you are generating the translation, right?
That's a good question. I think that I have to check back the paper to be sure that I'm not saying the wrong thing. But what I think is that it's bidirectional, so you have to consider for each element in the output what element of the input has been used to produce this part of the output. And what is said in the paper that I mentioned is that you have a better correlation with this kind of explanation provided by attention. You have a better correlation between attention and other explanation techniques. So it's not saying that the explanations are better, for instance, for users and other ways to evaluate explanations, but it's saying that you have a better correlation between different techniques in this setup. That's really important because it was one of the first arguments against attention, which was that attention did not correlate with saliency maps and other explanation techniques.
Yeah, but it's because when you are generating the translation of one token, you can infer which token in the output leads to this translation, but the token you generate do not affect the representation of your input. So it's only unidirectional, right? And so it's maybe that it's just easier to compute the weights, like to understand the relation between the attention weight and the outcome. That makes sense. Like the decision is less complicated to make because there is less cyclic relation between the input and the output. If that makes any sense.
I'm not sure I understand. So the thing that I am mentioning with attention, and tell me if we're not talking about the same thing, is that for each input token, so for instance, you are making a translation from, let's say, English to French. So you are consider for the first word in English, you are considering this word and all of the words, and you try to translate it in the first word in the target language. And you do that for the second word too. So you consider it this second word and the other word, and you translate it in another word. So you will for each word in the output, you will see what are the importance of the different words in the input language.
Yeah, I understand. It's just that what you are generating, like the first token, do not impact the representation of your input tokens. Mm-hmm. Whereas if you have only one sequence, then you have bidirectional attention, and each token is affecting every other token within the sequence. And so it might be way harder to understand what is happening because there is too many
or by bidirectional, you mean the embedding in the input. So you are embedding in one way of the sentence and then in the reverse way. That's what you were saying?
Yeah.
Okay, I thought you were saying in both way, like input output or output input. Okay, bidirectional.
No. So even in translation, you're when you are coding your input, it will be bidirectional. So this is not really understandable. But then inferring which part of the input causes the output, it is easier because you have less relation or interconnection between the two.
Yeah, I see what you're, sorry, I just see now what you are saying. Okay, with the bidirectional thing, I was not thinking about the same thing, but what you were saying is like, I think it's really right. I'm not sure about that because I didn't read it that explicitly, so I cannot say if you are right or not, but it makes sense, yeah. So maybe that's the reason why it's easier to have an explanation that's correlated with other techniques with multiple sequences. Maybe that's the reason. Yeah, I cannot be sure about that.
Yeah, sure. Thank you.
I have a question about evaluation. So you say that there are different ways to evaluate the explainability, but I don't see really, apart from the human-based one, what are the other ways to assess explainability?
Yeah, so that's a very important question. So the other part is the faithfulness. So how close is the explanation to the black box itself? And as I said, it's very difficult to find a way to provide an evaluation measure for that. It's really difficult. So one thing that I mentioned several times without saying that it was for faithfulness is the correlation between the methods. So if the different explanation methods are correlated with each other, that means something about faithfulness. So it's like saying if different people are explaining an event in the same way, maybe they're really explaining the event itself. But it's very difficult to find a way to assess explanations without users. It's very difficult. So I've seen papers where they try to use syntactic data, so they know what the model will learn. So you don't have access to the black box, but by designing your data, you know that the model will learn the things that you designed. And so you have the ground truth. And then you try to explain the black box, and you expect the thing that you designed in the data. But even in that case, you cannot be sure that the model did something completely different. Because as I said, the basic problem is that you have a black box, you cannot access the inner workings of the black box. So by definition, you cannot have the ground truth about what the black box is doing. So that's a very, very difficult question. And the users alone are not sufficient to assess faithfulness. As I mentioned in my presentation, there are papers that show that you can, in fact, mislead users by thinking that the explanation is good, why it's not, in fact, faithful to what the model is doing.
Okay, thank you. You said that you said several times that we consider the correlation between different models for explainability, but you also say that, if I understand right, usually or often these models are don't agree on an explanation, and that's a problem.
Yeah, that's something that has been shown by one paper. But at first, in fact, what papers did is they took one explanation technique that they considered good. So let's say a gradient-based explanation, because you use the gradients inside the model, so maybe that's the ground truth. So you use gradient-based explanations, and you compare that to the explanation technique that you want to assess, in our case, attention. And if it's not correlated, then you will say it's not a good explanation. The explanation is not faithful, because I could compare it to an explanation method that I consider ground true, and they are not correlated. So this thing was done before. And then there are papers that analyze the fact that the different methods between themselves do not correlate with each other, so we cannot use this way to evaluate faithfulness. So what I meant with your previous question is that there are multiple ways to assess faithfulness, but none of them are really good, because they all have flaws, because you cannot access the ground truth. So you can use some techniques or methods to evaluate faithfulness, but you will always have flaws in your way you evaluate faithfulness. And in this case, it's a very big flaw, because as you mentioned, the techniques are not correlated with each other. But we didn't know that before the paper that analyzed that.
Okay. Okay, thank you very much.
I have a question. So I have the feeling that in the end, nobody is claiming that attention is explanation. Some people say it's not the case at all, or it's the case but to a very, very, very small extent, or that it's the case with a different meaning of explanation, a different definition. Some of us say this is imposed because we cannot measure it, or we cannot define explanation. So in the end, nobody is claiming that attention is explanation, right?
Yeah, that's right. In fact, that's partially right. In fact, some papers, as you said, are saying in some cases it can be explanation, but in other cases it's not. But there are few papers, very few papers that are saying, okay, in our experiments, it shows that attention is explanation. There are very few papers. But what's interesting is that before this debate, most papers considered attention as a way to explain the model. So just before 2019, you could find many papers using attention as explanation.
Ah, okay. But it was a mistake because attention was not designed for this.
Yeah, no, it's a mistake in the sense that when you are trying to evaluate if it's explanation, you will see that it's not, like many have seen and in the papers that I presented. But the intuition at start was, okay, we use that for performance, but it somehow carries something about what the model is doing. So we can use that as an explanation. And you can find many papers, even now, I think, that do not consider this debate and that consider attention as an explanation.
Okay. So there's a real debate. Okay.
But in fact, just to add something, I think that attention can be interesting for explaining the model because it's something that's learned with the model. It's just that you cannot use it like that in the model. So like it's defined now. You need to add things like terms in the objective function or weights somewhere or new parameters. You have to add something to the way attention is defined right now to make it really attention. You cannot use it as it is defined right now.
Okay.
Thank you.
Thank you very much for this beautiful talk.
Thank you.
I hope everything goes right in Colorado, and we wish you a very pleasant day. Our day is finished, your day is starting. Okay?
Yeah. Thank you very much for having me. Thank you.
Okay. Bye-bye.
Thank you.
Bye.
Goodbye.
Bye.